Hello everybody and welcome back. We're going to continue our look at the 2013 Friar. We've been looking at it all along and we've come to the last question on the paper, so this will be the last in the series of videos for the 2013 Friar. And then, who knows, maybe you'll join me for another paper, maybe another Friar, maybe another type of paper altogether. Who knows? But let's take a look at question number 4. Alright, so hopefully you've had a look at this question already. You tried it. You should always try the contest questions ahead of time. That's why there's a link provided in the description to these contests on the CEMC website. A dot starts in the XY plane at 0, 0, and it makes a series of moves. In each move, the dot travels 1 unit either left, right, up, or down. 5 of the many different ways that the dot could end up at the point 1, 1 are go up 1 and over 1 and up 1, down 1, so those cancel out and he's basically back to the starting point, then over 1, up 1, up 1, so it goes up 2, over 1, and then down 1, and that'll get him to 1, 1, and up, over, and then back. So these last 2 steps sort of cancel each other out. Alright, so we have 4 parts, just like we did in part 3, or in question 3. So A, in how many different ways can the dot end up at the point 1, 0 in 4 or fewer moves? Okay, 4 or fewer moves. So maybe it might help to draw a little bit of a grid. Maybe it might help if I could keep my hand steady for a second. All right. So the question tells us it starts at 0, 0. And we want to get to 1, 0. So that's, let's say he's over here. And we want to use 4 or fewer moves. Okay. So we can get there in exactly one move, only one way. Pretty clear that just moving to the right will get us there, and that's the only way to do it in one move. But what about other moves? What about 2 moves, or 3 moves, or 4 moves? Okay. Well, so if we go up at any point, we'll have a y coordinate of 1, for example. We'll have to have a corresponding down movement to get us back to a y coordinate of 0. Okay. Similarly, it's not hard to see that we must go right 1 more times than we go left. These are sort of general observations we can make. If we want to just move over to the left one, all our ups and downs will need to cancel, and all our left and rights will need to cancel, except for 1 right. We need to move right by 1. So, what does this tell us? every other symbol other than exactly one of the right movements cancels out with sort of its opposite symbol. So the only way to get to 1, 0 is by using an odd number of moves. You need to go over 1, and then every other symbol has a pair. So we can divide, there'll be an even number of all the other symbols. So if we were to use 3 symbols, we already know how to do it in 1. 3 symbols, we either have an up, a down, and a right, or 2 rights and a left. However, we can rearrange all of these to get completely different ways of getting there. So we use factorials, permutations, and sort of combinatorics notation, and we can figure out how many different ways we can arrange these symbols. Well, there's 3 factorial. There's 3 choices for what the first symbol out of these 3 can be. You know, maybe we put the down first, and then 2 choices for the remaining symbol. Maybe it's the right, and then that leaves us with the up left over. So we get 6 different ways we can arrange these symbols. So that gives us 6 different ways to arrive at 1, 0. Okay. So the only things that matter to get to our final destination are the number of each symbol. Not the order in which we travel. Okay, so all 6 of these will still get us to 1, 0. Now how about this? So if we have 2 to the right and 1 to the left, well, there's a special notation for this. We'll write the answer first. So there are going to be 3 ways to rearrange these. It's all about where is this left guy going. But here's a bit of math knowledge if you're not aware of this already. We have n objects to arrange. And we have n1 of them are object 1, so maybe n1 of them are the letter A. So maybe 3 of them are the letter A, 2 of them are the letter B, and 5 of them are the letter C, and we have 10 objects to arrange. Well, there's a formula for the number of ways we can uniquely arrange these. all of object 1 look identical, so there's no way to distinguish between them. So we don't want to count multiple copies of the same arrangement. N factorial over n1 factorial times n2 factorial times nk factorial. And that's the general way to arrange n objects where you have identical copies. Okay. It's actually a lot of writing for the single written question, but hopefully some of the theory that we're using to solve this question is nice setup for B, C, and D, whatever those questions are. So we have exactly 10 ways to get to 1, 0. Now, considering that it's a light bulb, we didn't need to write out all this theory. We could have just really guess and checked. There's only 10 of them that we needed to do. So that's how many different ways the dot can end at the point 1, 0 in 4 or fewer moves. If we had 5, that's another odd number. There'd be more possible things, more sequences of ups, downs, lefts, rights that we could be trying. All right, B. At how many different points can the dot end in exactly 4 moves? Okay, so in exactly 4 moves. So, well, I have a way I think I could answer this, but it involves developing a bit more theory. So let's see whether or not that might be useful by reading C and D. You get a good sense of what you're going to need for C and D if you read them, and then A, B, and usually C are the earlier questions are supposed to help you solve the later questions. So you can try and look for patterns and develop theory in A and B that might help you solve C and D. So I have an idea. It might be useful. It's going to involve like some of the coordinates for the possible values. But let's see what C and D have. So determine with justification the number of integers k with k less than 100 for which the dot can end up at the point negative 712 in exactly k moves. Okay. So that's similar to this one. We're talking about exactly 4 moves. But we're given a specific point, not the different points. The dot can end up at exactly 2,304 points in exactly 47 moves. Determine with justification the number of points at which the dot can end in exactly 49 moves. So this is talking about number of points in an exactly, so number of points in exactly a certain number of moves. And then it's asking us for number of points in exactly a certain number of moves. So it might be helpful to be able to actually tell which points you can end up in a certain number of moves. So we're going to develop a general theory. So theory just means sort of idea, guess, but we're going to show that this should be right. So we're going to show where the dot can end up after. Actually, let's call it n because I think C uses k, and I don't quite remember if this is exact. Okay. So the guess that I had was sort of we needed to do an odd number of steps to get to 1, 0, which has a sum of coordinates being odd. To get to 0, 0, we could use no steps. We could go up and down, cancel that out. That's 2 steps. We could go left and right, cancel that out. Those two cancel each other out. That's 2 steps. Or we could go up, down, left, right. You can't really get to 0, 0 using an odd number of moves. It's sort of to stay at the origin, you have to every move you do, you have to be able to cancel it out. So that idea gives us a sort of a pair of moves. So that's our idea, is that to get to 1, 0 or 0, negative 3 or 5, 4, since the sums of those coordinates are odd, we're going to need to use an odd number of moves. Okay. So how would we show this? Let A be the number of rights, B number of lefts, C the number of ups, and D the number of downs. So if we want to be over by 1, we need one more right than left. And that's really saying that A minus B is equal to X. Okay? And if we're up by 3, we need 3 more ups than downs. So y is c minus d. Okay. So where's that gonna get us? So that tells us that x plus y, if that's even or odd, that's the same as a minus b plus c minus d. Now the total number of moves is a plus b plus c plus d. But that's just a minus b plus 2b plus c minus d plus 2d, which is x plus y plus some even number. And if you differ by an even number, then either you're both odd or you're both even. So fantastic. So what we set out to prove, if x plus y is an odd number, you need an odd number of moves to get to x plus y. If it's an even number of moves, you need an even number of moves to get to x plus y if x plus to xy if x plus y is even. So x plus y odd, you're gonna definitely have an odd number of moves to get there. If x plus y is even, you'll need an even number of moves. Okay. So that tells me exactly what kind of dots I could end up on in 4 moves. In 4 moves, I can end up at any even sum. So 5, 1, 6, 2, a billion, and 0. Our theory is not quite complete. Even number of moves, I know which ones I could be on and which ones I can't be on. But exactly which ones I can get to is another story altogether. So another idea, what's the minimum number of moves? So to get to point xy, if you haven't seen this notation before, it's absolute value of x plus absolute value of y. Basically, we just ignore the minus signs. So the absolute value of minus 3 is 3, the absolute value of 7 is 7, the absolute value of 0 is 0, the absolute value of minus 9 is 9. That sort of stuff. So we need at least absolute value of x plus absolute value of y moves to get to xy. That's what we claim. So we know x is equal to a minus b and y is equal to c minus d. So how exactly do we want to do this? I know what I want to say, I just don't want to write it in too long or too weird of a way. Basically, I want to say we can just assume x and y are positive for this example. Yeah, okay. I think I know what I want to say. So if x is negative, then the absolute value of x is actually b minus a. Because we need to make a minus b, which is x, into a positive thing, so we multiply the whole thing by negative 1. But to make our lives easy, we're just going to assume x and y are positive. If not, we could carry out the exact same reasoning. And if you're absolutely sure that it's the exact same reasoning, but for a tiny little notational tweak, you can write something like this in the contest. They're perfectly trained, the markers are perfectly trained to understand stuff like this. Okay? So you can, that way, instead of writing out 4 different cases where x is positive and y is negative, or y is positive and x is negative, or they're both negative, or they're both positive, we can just sort of write out one reasoning that works for all of them, modulo some, accepting some minor notational differences. So then the absolute value of x plus the absolute value of y is a minus b plus c minus d. But b and d are at, they can't be negative. You can't have a negative number of lefts or rights or something like that. So a total number of moves, which is a plus b plus c plus d, must be greater than or equal to absolute value of x plus absolute value of y. So we know that x, absolute value of x plus absolute value of y is at least needed. It's at least it's upper bounded by the total number of moves. Now we want to show that you could use exactly absolute value of x, absolute value of y moves to get there. So in this case, where we assumed x and y were positive, we let a just be the value of x and c be the value of y. If x had been positive and y had been negative, we'd let a be x and d be y. But the point is, these will give us the same number, the right number of moves, and we will exactly reach x and y. No more explanation needed there. Oh, you know what? We need one other little fact. So we've shown that if x and y add up to an even number, you can get there in exactly x plus y, which is an even number, and it's a potential. But what if it was any old even number? So we can get there in exactly n plus 2 moves. So whatever you did to get there in n moves, just add an up and down. And that'll give us n plus 2 moves. So if we want to put these facts together, and how many dots can we get to in exactly n moves? So we need x, absolute value of x plus the absolute value of y. That'll be even if x plus y is even, so we don't need to worry about that. So we can get to any location where the absolute value of x and y is less than or equal to n, and has the same oddness or evenness as n. That's exactly what we're saying here. So we can get to exactly these locations, 0, 2, and 4 being the absolute values of x and y. So, what does that tell us? Sum of the absolute values is 0. X and y are going to be 0. How about the sum of these values being equal to 2? Well, we could have 0 plus 2, 1 plus 1, or 2 plus 0. So that's 0, negative 2, 0, 2, 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1, 2, 0, or negative 2, 0. How about 4? Well, we have lots of different ways we can do this. And then finally 4 plus 0. Now this is also going to be fairly long to work out. So the question is, can we work out a better way of doing it? So if x and y are both 0 for our sum. So if these guys are 0, we get 1 spot. So if x is 0, absolute value of y not 0, we get 2 spots. Same with absolute value of x not equal to 0, but absolute value of y equal to 0. 2 spots, we get 0, y, 0, negative y. And here we'd have x0, negative x0. And then finally, we'd have if absolute value of x is not equal to 0 and absolute value of y is not equal to 0, we'd have 4 spots we can get to. Xy, negative xy, x negative y, negative x, negative y. Okay, so that might make things a little easier. So what we're going to do is we're actually just going to restart this part of the question over again. Alright, so we would have x plus y can be equal to 0, and 2 or 4. Okay, so x plus y equal to 0, that gives us 1. So that can be 0 plus 0. So that's 1. X plus y equal to 2. We could have 2 plus 0. That gives us 2 spots. We could have 1 plus 1, and that gives us 4. Or we can have 0 plus 2. That gives us 2. How about 4? Well, we got 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, and 0 plus 4. And that gives us 2, 4, 4, 4, 2. Okay. And if we add all that up, we get 1 plus, that's 8, and then that's 16, 25. Okay. So that gives us 25 different ways of doing it. Now, frankly, that was a lot of theory for very little gain on this part of the question. So I'm wondering if we could We did a lot of theory there. I'm wondering if we could notice a pattern here. So if k is 0, we get one way of doing it. If k is not equal to 0, we get two 2's, and then k minus 1 4's, which is going to be equal to 4k. So if we have n is odd, what we can do is we can actually generalize this and say, if we're trying to get an absolute value of x plus absolute value of y to be exactly k, other than if k is 0, we're going to have 4k different x and y that solve this. So we can use that and say, now, if n is odd, the number of ways we can get to xy, number of xy's we can get to in exactly n moves, well, we could go. There's four different places we can get to with an absolute value of 1. 4 different places we can get to with an absolute value sum of 3. All the way up to 4 different places we can get to with an absolute value, or 4n different places we can get to with an absolute value of sum of n. And that gives us 4 times 1 plus 3 plus all the way up to n. But that has a formula. That is 4 times n minus 1 over 2 squared. It's n plus 1, sorry. That gives us n plus 1 over 2 squared. So if n is odd, we have a nice little formula. How about if n is even? Well, we'd have 1 for the 0, plus 4 times 2, plus 4 times 4, all the way up to 4 times n. Okay, well that's 1 plus 4 times 2 plus 4 plus n. 1 times 4, 1 plus 4 times 2 times 1 plus 2 plus all the way up to n divided by 2. Remember, n is even. 1 plus 8 times 1 plus 2 plus all the way up to n divided by 2. And there's a formula for that. Sum of the first n over 2 natural numbers, that's n times n over 2, or n over 2 times n over 2 plus 1 all over 2. So that's going to be 1 plus, that'll cancel out, those will cancel out, so 2n and over 2 plus 1. Yeah. Okay. And that n squared plus 2n plus 1 is n plus 1 squared. So this should definitely help us for D part. Now I know we just solved B, and there's definitely a C part we need to do, but this is actually kind of exciting. N plus 1 squared. And if we go back and check, that squares with what we just figured out. To get to 4, we would have 25. Alright, so that definitely does B, and actually probably sets us up really nicely for D. But we still have this pesky C in the middle. Alright, determine, with justification, the number of integers k with k less than or equal to 100, for which the dot can end up at the point -7 plus 12 in exactly k moves. Well, hey, we sort of already know how to do this. We know that k is going to have the same parity, the same oddness or evenness, as the sum of the coordinates, -7 plus 12. Okay? We also know that k is at least as big as the absolute value of the coordinates. And that's 19. So 19 less than k less than or equal to 100. So k has the same parity as -7 plus 12. Remember, parity just means oddness or evenness. It's the fancy way of saying it, so we don't have to keep saying even and odd. But that's 5. And we know that any k value in this range will work. We know that at least 19, and we know how to get 21 or 23. We know how to get every odd number. We developed this entire theory already. So how many odds are there between 19 and 100? What am I thinking here? So let's let k equal 2m plus 1. We want to count the number of possible values of m that work here. 19 less than or equal to 2m plus 1 less than or equal to 100. So 18 less than or equal to 2m less than or equal to 99. Really, it's going to be 99. We can't have k be even. We already showed that. Alright, so that's going to be 98. So that means 9 less than or equal to k, less than or equal to, so 98 divided by 2, that's 49. So we want to count the number of numbers. Oh, sorry, that's m. And that equal sign is way too high. There we go. So the number of possible k values is just the same as the number of m. And that's the same as the number of numbers from 1 to 49 inclusive. Well, there's a formula for that. We take the two numbers, we take their difference, we add 1. We have 41, so 41 is the k values. And we were just asked for the number, not the actual one. Determine with justification the number of integers k. There we go. Thanks to our earlier developed theory. All right, now D part. The thing that we sort of worked out, that extra little bit after part B, that in n moves you can get to exactly n plus 1 squared locations. That's going to make D a breeze. So the dot can end in exactly 2304 points in exactly 47 moves. Well, let's check. Does that work with our theory? 47 plus 1 is 48. And if we were to square that, we'd get 2304. So that matches with our theory perfectly. Determine with justification the number of points at which the dot can end in exactly 49 moves. (49 plus 1 squared), that's 50 squared, so that's 2,500. Right, so a single sentence solution there, thanks to our previous work. Thanks to all that lengthy computation we did here to get that both answers were just n plus 1 squared. This extra specific casework that led us to that. These three ideas that gave us our general theory of, how many moves does it take to get somewhere, how many sorts of moves can you use to get there. That's great. I bet there's a whole bunch more theory that we could probably develop. Like, we could probably come up with the number of different ways you can get there using some general theory. But it was a nice, interesting exercise in parity, at least for a little bit of this. And then I'm really happy that our formulas worked out nicely. Both the odd and even formulas were the same. And these last two questions, the C and D, the really hard written parts in the hardest question in the problem set, were made so much easier by stopping and just taking a look at a bit of extra theory. I really like it when a question comes together like that. Now, it probably took me a lot longer than you would want it to on a contest problem, but remember, I am talking to you guys. I am trying to slowly write things out so you guys can keep track. So if you're experienced, if you practice these things, you'll be writing them out. You'll be thinking a lot quicker than I do, and you'll be writing them out a lot faster than I do. So don't get discouraged if this video is however long. It just, I'm trying to explain, I'm trying to teach, and share a little bit of the motivation going on in my head. Unfortunately, it takes a long time to speak that out rather than just think it. So this is easily achievable sort of work that you could be showing on the contest. And remember, to count the number of points each part should likely be worth. No, in a 4-part question, nothing should be worth more than 4 at the worst. So, be mindful of that and show as much work as you need to reasonably get 4 marks. And after you've done enough of these contests, and if you go on to mark these contests or mark similar papers, you'll get a sense of where the marks really are. Yeah, but that concludes the 2013 Friar. I think it was an excellent paper. Maybe, I mean, I had a little bit of a beef with, you know, maybe it took me a little while to figure out some little bits on some of the other parts of the questions. But I think overall, excellent year, excellent contest. And yeah, so that's 2013. Hopefully you'll join me for the 2014 or maybe the 2013 Galois and Hypatias. You can find all this sort of stuff on my channel, so like, subscribe, do whatever you want, and I hope to see you guys in the next video. So, sayonara.